So, we're going to continue our discussion about significant figures. Let's say that you're doing a lab and you put something on a scale and it tells you that the object is 326 grams. And you're going to be asked, well, how many significant figures is that value, that measurement? It's pretty evident. You're going to have to trust the instrument. You're going to have to believe that the instrument is giving you the correct amount of significant figures. And in this case, 326 grams, 3 significant figures. For whatever reason, this particular scale only reads to the nearest gram, and the scale isn't to be trusted beyond that measurement in more of a fractional way. So now if you take that same object and put that same object on a different scale, a more precise scale, perhaps on a second scale, 325.7 grams. Maybe on a second scale, it can read the 10th place. And so now, on this scale, you would have 4 significant figures. So you're going to trust the instrument. Sometimes we don't do the direct measurements. Sometimes we get handed measurements by other people, or other scientists publish data and have it peer reviewed in their area. When you receive a value, a measurement, you're to assume that they use the theory of significant figures and the practice of guessing the numbers correctly. And so you are just to read a number and try to determine, at times, how many significant figures are being used. To what precision are these measurements? For instance, you could be told that something is 1.74 meters long. You're going to be asked, well, how many significant figures is this? Well, there's 3 digits. You're to assume three significant figures. And that would mean that these 2 are the known values that we absolutely can be assured of, and then the last digit, the 4, is a guessed position. A guessed, we weren't sure. It was really a 1.74, or 1.73, or 1.75. For whatever reason, the person doing the measurement believed that was roughly a 4. 3 sig figs. If you get a measurement, say somebody puts something on a scale and they're going to tell you that it's 510 grams. This gets a little tricky. So you have to assume the scientist is writing it correctly. If they're writing it correctly, this 510 grams is not 3 significant figures. It's 2 significant figures. What this is saying is that, look, we knew it was 500 grams at least. And we knew it was near 510, but we weren't 100% sure. But we knew it wasn't quite 520, and we knew it wasn't close enough to 500. So instead of spacing things by 1, we're spacing things by units of 10. So for whatever reason, that scale wasn't, we couldn't zero in on that scale very well. This 0 is not significant. It's what we call a placeholder. There's a way to know that. They didn't put a decimal there, or they didn't write it in another way. So hold on to that thought. I'm going to show you the difference in a minute. Let's say that we get another measurement, another example. Let's say we have a measurement at 0.001 0.036 seconds. Let's say something happens really fast. And you're like, okay, how many significant figures is that? 4? No. 3? No. Just like you can have zeros as placeholders in front of the decimal, you can have zeros as placeholders behind the decimal. So this thing happened so fast, we knew it happened between 0.03 and 0.04 seconds. And we thought it happened a little closer to 0.04 seconds than we could guess. We knew the 0.3 was there. And so whomever took the measurement, or whatever measuring instrument it was, said, okay, well, it's a little closer to 0.04 seconds, but not quite there. And these zeros end up just being placeholders to get us there. And when it's written like this, sometimes it's tough to tell what zeros are placeholders and what zeros are not. So what we can do is write everything in scientific notation, which is, but it really highlights significant figures. This can be rewritten as 5.1 times 10 to the second grams. Now, it's awkward, but what this does is, notice, if I move and multiply 5.1 times 100, I'll come up with 510. But it doesn't need that 0 there. The 0 doesn't need to hold that place. Because if the 0 wasn't here, it'd be 51 grams. It's nowhere near 510. So scientific notation really does help identify significant figures, because the times 10 to the whatever, that doesn't count towards the significant figure. Same thing with this. This could be 3.6 times 10 to the negative 2 seconds. Again, not very friendly looking, but again, if you ignore the times 10 to the whatever, 3.6, that's 2 significant figures. This can get really useful when we have stuff like this. If you have, like, I'll make up a number, 71,020 miles. How many sig figs is that? Well, what 0 is a placeholder, what 0 isn't? Well, if you write scientific notation accordingly, scientific notation, remember, you move the decimal, move it over. You always have to have one digit in front of the decimal and all the other digits are behind. This 0 has to stay because it's got to hold that place. That 2 is going to go, but this 0 isn't needed anymore. And you moved it 1, 2, 3, 4 spots. So that is 4 significant figures. Same thing happens here. If I had, say, 0.00078,350. Actually, let me change that. 78. That's fine, 50. Sorry, I had a moment. Let's say again this was seconds. It's happening really fast. How many sig figs? What zeros are placed and what placeholders and what zeros aren't? Well, I can move the 0. I'm sorry, move the decimal to put it in scientific notation. Keep one number out front. 8, 5. This 0 though needs to stay. Absolutely. The zeros in front are placeholders with small numbers. The zeros in the back are placeholders in large numbers. But this 0 here, you have to keep. What that's saying is, we were pretty certain that when we got to the end of this measurement, that we didn't really need to guess anymore. I'll show you that in a minute. Times 10 to the 1, 2, 3, 4. Negative 4.